All right, welcome to The Explainer. I am so thrilled you're here today. We're going to dive right in and master the actual mechanics of our natural world. We'll be taking this incredible journey from the deep, molten center of our planet, right up through the structures we build, the heat that drives literally everything, the plants that fuel life, and finally, those super delicate ecosystems we all rely on. So, let's just get right into it.
Okay, so what connects a devastating earthquake, a bicycle frame, and a sunflower? I know, it sounds kind of like a weird riddle, right? But stick with me here, because I promise you, by the end of this explainer, you're going to see exactly how these are all intertwined parts of one single overarching system. They're all governed by the exact same rules of energy, forces, and interconnectedness.
So here's our roadmap for today. We're going to build this logically, literally from the ground up. We'll start with planet Earth's moving pieces, then look at forces and strong structures. From there, we move into heat and moving particles, explore the power of plants, and then wrap the whole shebang up with interconnected ecosystems.
All right, let's start with the literal foundation beneath our feet. Section 1, Planet Earth's moving pieces.
You know, it's easy to think of our planet as just one giant, solid rock, but it's really not. Thanks to the theory of plate tectonics, we know Earth's crust is actually split into these massive segments called tectonic plates. And they aren't just sitting there. They are constantly, slowly shifting and sliding over the deeper, way hotter layers right beneath them.
To really wrap your head around the scale of this, think about it like this. The solid crust that we actually live on is unbelievably thin. We're talking only 5 to 60 kilometers thick. It's like the skin of an apple. Directly beneath that is the mantle, which is a massive 2,900 kilometers thick. And while the upper part of the mantle is solid, the lower mantle is actually molten liquid. Below that, we hit the liquid outer core at 2,200 kilometers, and finally, the solid inner core at 1,250 kilometers. So we're basically just cruising around on a super thin, solid shell that's floating above massive, shifting molten layers. Crazy, right?
Which naturally brings up a pretty huge question. How on earth do we build safely on top of all these moving plates? And that brings us to Section 2, Forces and Strong Structures. Think about any structure we create. Whether it's something as simple as a bicycle frame or as massive as a suspension bridge, it has to handle some really intense internal forces. When a force pushes down on the middle of a beam, for example, the structure actually experiences complementary forces at the exact same time. The top of the beam is physically being squeezed together while the bottom is actively being stretched apart. Understanding those two forces is absolutely key to knowing why things break. Compression is that internal force squeezing an object together, right? While tension is the force stretching it apart. When these forces just get to be too much, a structure starts experiencing what we call structural stress. If that stress causes a permanent change, like a crack or a weird bend, that's structural fatigue. And if the thing can literally no longer do its job, well, that's complete structural failure.
Now, to keep that failure from happening, engineers rely on this brilliant concept called a margin of safety. Basically, it means building a structure to be extra strong, way stronger than it technically needs to be, just to guarantee our safety. But it also has a super practical side, because it can be a limit set to make sure we use a structure safely. Think of a speed limit on a highway. That is a literal margin of safety applied to dynamic, moving loads just to keep all of us safe.
Okay, so we know the liquid mantle moves our tectonic plates, and we know the structures we build face immense stress from loads and gravity. But what's driving all this energy in the first place? Let's dive into Section 3, Heat and Moving Particles.
To truly understand these massive forces happening on Earth, we actually have to zoom all the way down to the microscopic level. The particle model of matter has 4 strict rules, and they're pretty straightforward. 1. All substances are made of tiny particles. 2. Those particles are always in motion, always. 3. They have spaces between them. And 4. There are specific forces of attraction between them. You definitely want to keep these rules in the back of your mind, because they basically explain everything about how energy moves around. All right, let's see those rules in action. Imagine a solid state. The particles are just kind of vibrating in place, right? They've got the lowest kinetic energy. But the second you add heat, you increase the thermal energy. Suddenly, those particles get way more kinetic energy, they start moving faster, bumping into each other more, and the spaces between them physically increase. This expansion turns the solid into a liquid, and eventually, if you keep adding heat, into a gas, where those particles are just zipping around freely with no definite shape or volume.
So the absolutely crucial part here is understanding how that heat actually moves. By definition, heat is just what happens when energy transfers from a substance or a particle with high kinetic energy over to one with low kinetic energy. Honestly, just think about sitting around a campfire. It's the perfect, cozy example that captures the 3 different ways heat transfer happens simultaneously in our everyday world.
Let's break those 3 down really quick. First, conduction. That's heat transferring through direct contact, usually in solids, like if you leave a metal poker in the fire and the handle gets hot. Convection happens in liquids and gases. Hot particles rise up, colder particles sink down, and it creates these circular currents. And then there's radiation, which transfers heat without needing any particles at all. It uses invisible infrared waves, like the heat radiating off the sun or the warmth you feel on your face from that campfire. And hey, remember those tectonic plates we talked about a few minutes ago? It is exactly these convection currents happening deep in the molten lower mantle that push and pull the Earth's crust. It all connects. So now we see how solar radiation brings this immense thermal energy to Earth. But how does life actually harness that heat? Welcome to Section 4, the power of plants.
Plants are, without a doubt, the ultimate solar-powered producers. It's incredible. They use this process called osmosis, where water moves from a high concentration out in the soil right into a lower concentration inside their roots. From there, they use photosynthesis. They take that water, mix it with carbon dioxide and the sun's radiant energy, and boom, they produce their own food, essentially sugars, while conveniently releasing oxygen into the air for us to breathe. Finally, through transpiration, any excess water just evaporates from the leaves through these tiny little openings called stomata, which actually creates a suction effect to pull even more water up from the roots. It is just this brilliant, self-sustaining biological engine.
And that plant energy? It's the foundation of all life. But where does it go from there? Well, this brings us to our final stop. Section 5, Interconnected Ecosystems, the Web of Life.
In literally any ecosystem, every single living thing has a niche, which is just a sciencey way of saying the specific role it plays. You've got producers, like our plants, making their own energy. Herbivores come along and eat the producers. Carnivores, they eat the herbivores. And then the decomposers, think bacteria and mushrooms, they do the cleanup, breaking down dead organisms, absorbing the nutrients, and returning them straight back to the soil. It's a remarkably fragile, perfectly balanced web.
Let's walk through a basic food chain to see this in action. The energy starts up at the sun, flows down to the seeds, then over to a snail. Maybe a bird eats the snail, a fox eats the bird, and eventually bacteria break down the fox. Now here is a super fascinating fact about this. The actual number of organisms, the biomass, decreases every time you move up a step in the chain. Why? Because energy is actually lost at every single level. I mean, think about it practically. It just wouldn't work to have 10 frogs trying to survive by eating only 5 grasshoppers. The energy math just simply does not add up.
But you know, there is a pretty dangerous consequence to being this interconnected. Because just like energy flows up the food chain, unfortunately, so do pollutants. Through these processes called bioaccumulation and biomagnification, the concentration of a toxic substance actually gets higher and higher as you move up through that chain. And what that means is top predators, and yes, that includes humans, are put at the absolute highest risk from environmental toxins. Which leaves us with one really vital question to think about. What is your ecological footprint, and how will you reduce it? Your footprint is basically the personal impact you are having on the Earth and the environment. Because in this massive, interconnected system we just explored, from those deep, moving tectonic plates, to the physical forces acting on our cities, to the heat of the sun and these super delicate food webs, every single action matters. Whether it's walking instead of driving, or just being mindful of the resources you use, how are you going to protect your specific niche in the natural world? Thank you so much for joining me for this explainer. Keep learning, stay curious, and I'll catch you next time.